All right, hi everyone. So today we are going to talk about calculus in physics. Now, you might have learned a little bit of calculus in your pre-calc class, especially if you had Miss Halstead for honors pre-calc. If you don't know any calculus, that is fine. This is why we were doing this lecture. But I apologize to your calculus teachers. I kind of give you like a down and dirty, just learn calculus really fast because we do need it for physics, for AP Physics. This is AP Physics C. The C stands for calculus, okay? Now, fun fact, calculus was actually invented for physics. So really, I think it actually makes more sense in the context of physics. So when you learn it in your calculus class, hopefully this will help you even learn it a little better. But I do apologize. I am not a calculus teacher, okay? So I am going to do my best to explain it in the best way possible. Again, this is probably going to be a very long video. So if you need to take a break halfway through, please do that. This is a lot of information in a very short amount of time, okay? But we do need it for class, and I want to get it to you for your summer work so we can start learning physics. So without further ado, let's get into it. So first and foremost, let's talk about slope. Now, in the Intro to Motion lecture that you should have watched before this, so if you haven't watched that yet, please go back, watch that one first, take notes, hopefully, and then you can come back to this one. Again, I talked about this in the Intro to Motion one. You can take notes on this. You don't have to. I would like you to take notes, but I'm not going to be grading them, okay? This is the college class. You are basically in charge of your own learning. Okay, you guys are almost adults here. So take notes if you want to. I highly suggest that you do. So like I talked about in the Intro to Motion lecture, when we have a displacement versus time graph like this, if we took the slope of this graph, we get rise over run. Rise is displacement over run, which is time. And so therefore we get displacement over time, which is average velocity. So again, slope is rise over run. Our slope will then be our average velocity because it's displacement over time. If we have a velocity versus time graph, so velocity on the y-axis, time on the x-axis, if we find our slope here, we get rise, which is change in velocity, over run, which is time. Change in velocity over time is our acceleration. Okay, so if I'm finding the slope of these graphs, I am finding either velocity on a displacement versus time graph or acceleration on a velocity versus time graph. Now, the trick here is that that slope was really easy to find when the line is straight, or we have a linear function. But what about when we have something a little bit more complicated? So something like this. We have a function where the line is curving. So it's really more difficult to find the slope. We can't just take the rise over run at this point. Now we could approximate and find an approximate slope at a certain time, but it's much harder to do. And especially if we want to find like the exact instantaneous velocity at say a time of t equals 2, we want to actually know how to do that with a slope that's constantly changing. So if we zoom in at that time of t equals 2 seconds, look, it looks like a straight line. Okay, so what we're going to do here is we are going to be zooming in. So if we zoom in, we get a straight line, and we know how to find the slope of a straight line. It's just rise over run. Super, super easy. So when we zoom in, what we're doing is we're shrinking the time interval, that change in time or delta t. We're shrinking it down. All right, we're finding the instantaneous velocity in this case because we have a position versus time graph, or position as it changes with time. So as the time interval approaches 0, the slope of the line at that point is the instantaneous velocity. And in the case for the graph to the right, the velocity at that instant of time equals 2 seconds. We talked about instantaneous velocity a little bit in the Intro to Motion lecture. Remember, this is also called the slope of the tangent line, or the line that's tangent to that point of the slope of the graph at time t equals 2. So that instantaneous velocity is the tangent line at that point. So it's easy to talk about, but the question here is, how do we actually find what that quantity is, or what maybe even the equation for the changing slope is as it relates to time? So the derivative is how we do this. The derivative is the instantaneous rate of change of a function with respect to one of the variables. This unit we're going to be talking about with respect to time only. Later in the year, we will be talking about different variables and taking the derivative with respect to position instead of time. But in this case, it's going to be just with respect to time. Okay. Now, this is a kind of confusing definition maybe at first. It's a lot of information in one little sentence. Okay, the instantaneous rate of change of a function with respect to one of its variables. So what we're getting here really, if I take the derivative and just what the derivative is it is how that slope is changing. So we're going to get a function of how the slope changes with time. All right, we already have how position changes with time, but when we take the derivative, we are going to get how the velocity or the slope is also changing with time. So this is equivalent to finding the slope of the tangent line to the function at a point. So in order to find the velocity at a specific point in time, we need to find the slope of that line that is tangent to the curve at that point. So what I've been giving as an example is t equals 2 seconds. All right, so if I find the slope of t equals 2 seconds, I can find the instantaneous velocity. But how do we do that with the function that is given? Right? We did an example where we approximated this instantaneous velocity or approximated the slope, but what if we want to know the exact instantaneous velocity at that time given that function? Okay, so how can I find the velocity at time t equals 2 seconds given that the position as it changes with time is equal to 5t minus 1 over 24 t cubed? We're going to take the derivative. All right, that's how we're going to do this. Now, we take the derivative using what we call the power rule. This is basically, you're going to lead up to this in calculus. So I'm just giving you the power rule. All right, you are going to learn more theory behind this, why it's done. When you are actually in calculus. Again, I am just teaching you the down and dirty calculus that you need to know for this class, right? So again, I apologize. Sometimes I say I use bad vocabulary when talking about calculus just because I was never trained to actually teach calculus. I just teach it in AP Physics. All right, so the power rule. This is the power rule. I know it looks really scary. Don't worry, okay? I'll walk you through it. This d over dx, you guys see this right here, d over dx. What this means is we are taking the derivative of this function right here, x to the nth power, n just means any number n, with respect to x. So in this case, in this unit, instead of x, we'll be using t, all right? But usually in examples, you always have a function as it relates to x or as it depends on x. In this unit, again, we're going to be depending on time. Okay, so you'll see d something over dt in our unit. What this means is you're taking the derivative of this function with respect to x. So when we do that, we're going to take this n right here, which just means any number, any exponent, and we're going to multiply the original function by that exponent. And then what you're going to do is you're just going to subtract 1 from the exponent. And that's it, right? That's the derivative. It gets a little bit more complicated, but we'll give some examples and I'll show you what I mean, okay? So this is my first example. I have the function is equal to 3x to the 5th. Now again, if I'm following my power rule, I take this exponent right here, I'm going to multiply 3 by that exponent, and I'm going to move myself over here. So I multiply by the exponent, so that's going to be 15, and then we're going to subtract 1 from the exponent. So that's going to be 5 minus 1, which is 4. So we end up getting 15x to the fourth, and that's our derivative of the original function. Now, again, if you've never seen derivatives before, you probably have not seen this notation either. This means the original function. This right here is what we call prime, that little apostrophe. So that just means f prime is the derivative. In physics, we don't really use this notation. We more are often are going to be using, I'm just moving myself all over the screen, it's fine. We're going to be using this notation right here. Because prime actually means something specific in physics. It means, if I remember correctly, it means with respect to time. So in this case, we could use prime, but something else actually means taking the derivative with respect to position. So usually we just kind of say we're taking the derivative with respect to whatever by saying d of the function over dt in our case, or dx in this example, okay? So let's do a couple more examples, and of course I'm gonna move myself over to the other side because now they're gonna show up over here. So another example, we have 5x squared. So again, we're taking our exponent right here. We're going to multiply 5 by our exponent and then subtract 1 from the exponent. So I get 5 times 2, because 2 was our exponent, times x. And then to the power of 2 minus 1, because I'm subtracting 1 from this exponent here, and we just end up getting 10x, because 2 minus 1 is just 1, x to the first power is just x. Second example, we now have 2 terms here, both with x in them. So it looks a little bit scarier, but don't worry, all you're going to do is take the derivative of each term one at a time. So the first one, we have 2 times x to the fifth. You take the 5, multiply 2 times 5, and then subtract 1 from 5. So again, we have 2 times 5, which is 10, x, and then 5 minus 1 is just 4. And then plus, and then we're going to take the derivative of 10x. Now again, x by itself is just like x to the first power, right? So we're going to take that 1, that imaginary 1 that's right here, we multiply 10 by 1, so 10 times 1, x, and then 1 minus 1, which is 0. So x to the 0 is just going to be 1. All right, so we end up getting 10x to the fourth for the first term plus just 10. Right, that x disappeared because we had x to the 0, which is just 1. So that's the derivative of example number 2. And then last but not least, again, we have 3 terms right here. So we have to take the derivative of 1 at a time. So the first one, we have x squared. Again, I'm going to multiply that exponent in front of that x. So I get 2x and then subtract 1. So I get 2x times and x to the first power, because 2 minus 1 is just 1, plus 5, and remember, we're going to pretend like there's a 1 on that exponent. So 5x to the first power, I take that 1, multiply that 5 by 1, and then subtract 1 from the exponent, so I end up getting x to the 0, which again is just 1. And then last but not least, look, I have just 3, so it's just a number. Now, in the case of just a number, what we can do is we can say that this is like 3 times 1, and remember, anything to the 0 power is 1. So this is like saying 3 times x to the 0 power. So if I take that 0 power from the x, multiply 3 by that, I get 0. So 3 times 0, and then times x to the 0 minus 1, which, yeah, is negative 1, but we're multiplying that by 0, so that term just goes away anyway. So what we get here is just 2x from that first term plus 5. So you can probably see a little bit of a pattern here so far. Whenever we have a, just like 10x, so whenever we have x to the first power, this 5x here, we end up just getting the number. So either the derivative of 10x is just 10, the derivative of 5x is just 5. And then when we have a constant like 3, just a number, the derivative of any constant like that is going to be 0. All right, so that's a couple little rules that you can remember here. So I know that was a lot of information, but let's do another example. Hopefully it will help you a little bit more to see an example of something that you would actually see in our physics class. Oh, never mind. That's going to be later on the next slide. So if we go back to our original function, and I'm going to take this derivative, the derivative of 5t, again, pretend like there's a 1 right here. We multiply 5 by 1 and then subtract 1 from that. So t to the 1 minus 1 is just t to the 0, which is 1. So we get 5 for the derivative of this part, minus 1 over 24 times t cubed. Again, take this 3 right here, multiply 1 over 24 times 3. So we get 3 over 24, which is just 1/8 if we reduce that fraction, and then times t to the 3 minus 1, which is just 2, so t squared. So our derivative ends up being 5 minus 1/8 t squared. Notice how I just changed what it's equal to. I didn't put, derivative of position with respect to time. I just changed it to velocity because remember, if we're taking the derivative of the position function with respect to time, we get velocity. If I take the derivative of the velocity function now with respect to time, I could get acceleration. I'm not going to do that. I'm going to do that in the next example, though, okay? All right, example number 1. So we have a particle's position on the x-axis is given by position as a function of time equals 4 minus 27t plus t cubed with x in meters and t in seconds. Because position x depends on time t, the particle must be moving. Find the particle's velocity function v, velocity, with respect to time, and acceleration function a with respect to time. So again, when we're going from position to velocity, all we're doing is we're taking the derivative. All right, so first and foremost, let's take the derivative of the original function. So we know velocity is the derivative of position. If we take the derivative of this original function here, I know the derivative of a constant is 0. So that just kind of drops out. And then I have this negative or minus 27t. So again, this is like t to the first power. I multiply 27 by 1, subtract 1 from this exponent, which then just gets rid of that t because it's just t to the 0. So I get negative 27 plus 3t. I'm taking this exponent, multiplying this whole thing by 3, and then subtracting 1 from 3. So I get 3t squared. So our velocity function is going to be negative 27 plus 3t squared. Now, if I want to know the acceleration function now, I know that acceleration is the derivative of velocity. We also call this a second derivative of position because to go from position to acceleration, you take 2 derivatives, all right? Second derivative, that's also another name for it. So we know the velocity function up there, just taking the derivative of the velocity function. Again, negative 27, this is just a constant. So the derivative of this number, any number, is just 0. So now we're just looking at this. Again, take this 2, multiply 3 by 2, so we get 6. Subtract 1 from the 2. 2 minus 1 is just 1, so we end up getting that the acceleration is 6t. And that's letter A, okay? Easy enough. All right, let's look at letter B. So it says now, is there ever a time where the object is stopped? So when an object is stopped, what equals 0? The velocity, right? Because it's at a standstill, it's stopped. So what we need to do here is we already found the equation for velocity. So now all we have to do is we have to set this equation equal to 0 and then solve for time, because for letter B, it's asking, is there ever a time where the object is stopped? So we'll find out. Let's just set our velocity equal to 0 here. So I plug in 0 for velocity. Remember this V and then with parentheses T just means velocity as it varies with time. All right, oops, you got a little preview. So plug in my 0 for velocity. That equals negative 27 plus 3t squared. I'm going to add 27 to both sides, divide by 3. I get 9 equals t squared, take the square root, and I end up getting that, yes, it is stopped at a time of 3 seconds. Easy stuff, easy stuff. All right, last but not least, we now want to describe the particle's motion for a time greater than or equal to 0. So at after we start timing, what does the particle do, basically? So for a problem like this, there's two ways to do this. You can either just plug numbers into the functions that you know and then kind of see what happens with the position, the velocity, and the acceleration, or you can also graph the equations. All right, we talked a little bit about graphing in the Intro to Motion lecture. So what I'm going to do here is I'm just going to plug in numbers, and guess what? I already did it for you just because for the sake of time. I don't even know how long this is so far, but I know it's going to be really long. So again, I have my position function with respect to time on the screen. Here's velocity and acceleration. What I did is I just plugged in times 0 all the way to 4 seconds. So here's the table of those values. And what you would do to answer a question like this is you would say something like this. Well, at a time t equals 0 seconds, the object starts at a positive position of 4 meters, say, and it is moving in the negative direction. So remember, negative velocity just gives the direction of velocity. So since it's a negative 27 meters per second, I'm just giving values. I think it did say, yeah, it did, with x in meters and t in seconds. So because it's a negative 27 meters per second, that means it's moving in the negative direction at a magnitude of velocity of 27 meters per second. Now, as the time goes on, the particle is slowing down while still moving in the negative direction. See how the magnitude of velocity is going down, but it's still negative. It then stops at a time of t equals 3 seconds in a position of negative 50 meters, turns around, and then moves in the positive direction while speeding up after 3 seconds. You can also talk about velocity if you wanted to. Remember, did I say velocity? You can talk about acceleration if you wanted to. Remember here, we know that we're slowing down because we have a negative velocity and a positive acceleration. When velocity and acceleration are opposite signs, the object is going to slow down. When they're the same sign, the object will speed up. So we can see here, when we have a positive velocity and a positive acceleration, the object is then going to speed up. If this acceleration was negative over here, then we would speed up, but it's not, and it never can be negative after a time of 0 seconds because look, it's 6t. So whatever positive time we have, which will be any time that we have after that 0 seconds, we're always going to have a positive acceleration. So after this, we're always going to be speeding up in the positive direction. Okay, so that's example number 1. All right, now that is your derivative. Okay, a lot of information in a little bit of time. So if it's still very scary and confusing for you, I am going to link some more videos about this that hopefully will help you a little bit. We are going to be using derivatives throughout this entire year. Okay, so I did want to introduce it early so we have a lot of practice for this. All right, next we're going to be talking about the area model. All right, so we talked about slope before, now let's talk about area. So another basic model for understanding graphs is area. Now, if I have this function, we know area is equal to base times height. So if I have my average velocity equation, which I know is delta, should say delta x, I don't know why I use this from the internet, but our displacement over time, if I rearrange this equation, I just multiply both sides by time, I get something that looks like this. So I get delta x, or displacement, is equal to delta t, or my time interval, times velocity, and that's average velocity in this case. So if I model this after the area model that I can see up there, area equals base times height, I can see delta x will be my area, delta t, or time, will be my base, and velocity will be my height. And this makes sense with a velocity versus time curve. When we have velocity on the y-axis, time on the x-axis, I have a base, my x-axis, with time, a height, my y-axis, with velocity, and so the area under that curve will then be displacement. We can also do this with acceleration. So I know average acceleration is equal to change in velocity over time. Rearranging this equation, we get our change in velocity is equal to time times acceleration, where change in velocity is the area, the delta t, or change in time, is the base, and acceleration is the height. All right, so this looks something like this on a curve. So if I wanted to know the displacement from t equals 0 to t equals 15 seconds. Again, I have a velocity versus time curve here. I know that velocity is equal to change in position over time, or displacement over time. Rearranging this equation right here, I get velocity times time equals my displacement, which is what I'm trying to find. So I know that velocity is on the y-axis, time is on the x-axis. So because of this, I can get displacement from this graph. It's going to be the area under the curve. So what I'm going to do now is I'm going to draw a line at that 15 seconds, and I know that in order to get my answer to this question, all I need to do is find the area under this curve. That will be my displacement from 0 to 15 seconds. Now this is kind of a weird shape. So what we're going to do here is we're actually just going to divide it into two shapes that are a little bit easier to find the areas for. So now I have a right triangle and I have a rectangle. So right triangle, the area for that is just 1/2 base times height. You can see the base for the triangle is going to be 10 minutes. The height is 60 meters per minute. So we get 1/2 base 10 times 60 height, plus the area for the rectangle, which the base is 5 and the height is 60. So doing this math, magic, is 600 meters. I hope I did that correctly. So our answer here is 600 meters. Now, what about if we have an acceleration versus time curve and we wanted to know the change in velocity during the time interval 2 to 5 seconds? Again, here's my equation for average acceleration. If I rearrange this, I get acceleration times time is our change in velocity. And so here what this tells me is that if I get the area under the curve from 2 to 5 seconds, then I'm going to get the change in velocity, because the area under the curve here is base, which is time, times height, which is acceleration. So time times acceleration, or acceleration times time, will be our change in velocity. So again, drawing my lines here, 2 to 5 seconds, I get, and really I could just plug in my acceleration there because it is constant, and then times time here. So I get 1 centimeter per second squared times 3 seconds equals 3 centimeters per second. So the base here is 3, the height is 1 in this case, and it's just a rectangle, so that makes it easy. Notice how this is not the velocity at a certain time. This is your change in velocity during this time interval. Okay, remember that. It's a very important distinction. If I did want to find the velocity at a time of 5 seconds, if I started from a velocity of 0, I would have to take the area here under this curve and the area here under this curve, and then add them together. And what do you think with this area? What's special about this area? If you said it's negative, you're correct, right? If it's in the negative down here, and really it's like the area over the curve, stupid, that is going to be a negative area, all right? So you would have to assign that a negative value in order to find the area. Same goes for velocity versus time. You can have a negative displacement as well. Now, again, just like we talked about with derivatives, it's really easy to do that if you have a linear function, right? We know how to find areas, or we know how to, areas of triangles, areas of rectangles and squares. It's very easy to do this if we have a linear function. However, what happens when we don't have a linear function? So how do we determine how far something travels when the velocity versus time function is a curve? Or what the change in velocity is when the acceleration versus time function is a curve? As the function varies continuously, determining the area is not as easy as it was before. So again, just like we did before, we are going to zoom in. So we're considering an arbitrary time t, which you can see on the x-axis down there. It's between t1 and t2. So we're placing a differential time interval dt about time t. What this means, dt, is kind of like a delta t, but it's just a very, 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 very small interval. You'll also hear me talk about this as like the word is infinitesimal time interval, meaning just super, super small time interval. So this rectangle is super small and is only visible for the purpose of this explanation, okay? We're talking about an instant. That time interval is an instant. Now, if I zoom in here, our rectangle looks like this. Now we can see that 1 is in the rectangle, but 2 is not. All right, so what we're doing here is if I just take that, oh my gosh, I keep getting in the way, I'm sorry. So with that dt being very, 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 very small, that area number 1 fits into area number 2 because area number 2 is under the curve, and we're taking the area under the curve, so that the approximate area is simply the area of a rectangle. So if we find all the areas for all the dt's between t1 and t2 and then add them all up, what we do here is we find the total area, which in this case would be displacement because we have a velocity versus time curve. All right, so if we have a way to do this, we can find the area under the curve. The idea here is that the area under the curve is the sum, and that's a very important word here, of all the areas of each individual dt. Now, sum notation, you might have heard of this from pre-calc. I don't know, honestly, I don't remember when you guys learned this now, but if you've seen that sigma symbol that's right here, or sideways, looks like a sideways M or a sideways W, that is the sum notation. All right, so the temptation here is to use that conventional summation sign, meaning we're summing up all of those little rectangles, the area of all those little rectangles. Now the problem with this is we can only use a summation sign to denote summing of discrete quantities and not for something that's continuously varying. So because of that, we use a different symbol. So when a continuous function is summed, the different sign is used, which is called an integral, and it looks like this. All right, so what we're doing here is we're just summing up all those areas under the curve when we use this integral sign right here. I call this, sometimes I'll call this the snake, a snake. Now, when you take an integral, this is also called taking an antiderivative. All right, so there's several names for this: integral, antiderivative. Sometimes I'll say the snake, just because, I don't know, it's more fun. So when we're dealing with this situation and we have to integrate, we need to realize that what we are given is the derivative and what we want is the original function, hence the name antiderivative. All right, we're going backwards. So what are we basically doing? We're working backwards to find the antiderivative. Okay, a lot of information. I know. So how to take the antiderivative? Looks like this, which again looks very, very scary. I know that looks very, very scary, but I'll take you step by step through it, okay? The antiderivative or integral is simply the opposite of the derivative, so we do the opposite of the power rule. So number 1, we're gonna take the exponent and add 1. So remember, with the power rule, we subtracted 1 from the exponent. With an antiderivative or anti-power rule, we are adding 1 to the exponent, hence this right here, n plus 1. And then we are going to divide by that whole thing. So we're dividing the entire function by n plus 1, all right? So what this notation looks like right here is we have the integral of x to the nth power with respect to x. Remember how we had d over dx for derivative? Now that looked like we were dividing by dx. Here we have times dx because this again is the opposite, right? We're taking the antiderivative, the anti-power rule. And then what we do here, again, we add 1 to the exponent and then divide by this whole thing. Now, this says plus c. There's a reason for that, okay? C stands for constant because remember, the derivative of a constant is 0. So the derivative of 3 is 0. The derivative of 1,000 is 0. The derivative of 1,000,000 is 0. The derivative of any just number or constant is 0. So because of that, when we're going backwards and we don't have anything on the end, there could have been a number there, but we just don't know what it was. So we have to add c to what we call an indefinite integral. Don't worry about that right now. I'll explain how to get rid of c or what we do with c in a bit. Okay. Notice also that this says for any n, any number that doesn't equal -1. The reason for this is because if n equaled -1 here, we'd have -1 plus 1, which is 0. We would then be dividing by 0, which is a no-no. We can't do that. Okay, we can't divide by 0. So if n equals -1, which would just mean that it's 1 over x, because we know x to the negative 1 is 1 over x. The antiderivative of 1 over x is just the natural log of x. You most likely will not be using that in this class, but that's just a rule that you should remember, okay? All right, so let's do an example. We have the integral of this function with respect to x. So I'm taking the antiderivative, or the integral of this function with respect to x. So what we're going to do here is we're going to take this step by step, just like we did with the derivative. So we're going to take that first term right there. I have 3x squared. I'm going to take that 2, add 1, and then divide the whole thing by that. So I have 3x to the 2 plus 1, because again, I am adding 1 to the exponent, and then I'm dividing that whole term by that new exponent, so 3. I'm then going to move on to the next term. So I have 4x to the first power. Remember, it's like a imaginary 1. I'm going to add 1 to that imaginary 1. So I get 4x to the 1 plus 1. And then I'm going to divide that whole thing by 1 plus 1, all right? Last but not least, I am going to take that final term, so just my 2, and then just like we did with the derivative, we want to pretend like this says 2x to the 0 power, because remember, x to the 0 power is just 1, so this is just 2 times 1. So 2x to the 0 power plus 1, and then we're going to divide that whole thing by 0 plus 1. And then, like I said before, we have to then add c, because there could have been another term in that in the original function before we took the derivative. There could have been any number there, but we don't know what it is because the derivative of just one number is just 0. All right, so now simplifying here, we get 3x cubed divided by 3, so that just becomes x cubed. We get 4x squared divided by 2, so that just becomes 2x squared. And then we get 2x divided by 1, so just 2x. So x cubed plus 2x squared plus 2x plus c, and that's our answer, okay? All right, let's do another example. I'm going to show you how you can actually solve for C, and oh, my dog just came in. And so the first example, I'm going to show you how C just kind of goes away, and then in a further example, I'm going to show you how you can actually solve for C itself, okay? So example number 2 says an object is moving at a velocity with respect to time according to the equation. Velocity with respect to time is equal to 2t. And then we want to know A, what is the displacement function? B, how far did it travel from 2 seconds to 7 seconds? All right, so we know that since we want to go from velocity to displacement, we have to take the antiderivative or the integral. So this is what the notation looks like, all right? We have displacement function, which is what we're trying to find for letter A. That is equal to the integral of the velocity function with respect to time. Notice how we're taking it with respect to time this time, not actual just x, which is what the examples have been showing, because this unit will be with respect to time. So now what we do is we plug that velocity function in here for v. So we're plugging that 2t in here. And again, we're taking the integral of 2t with respect to time to find that position function, okay? So again, using our rules, this is like t to the first power. We're going to add 1 to that 1, imaginary 1 that's there. So we get 2t squared, and then divide that whole thing by 2. So that ends up just being 2t squared divided by 2, which is just t squared. And again, we're not going to forget to write our c down, okay? Now, that's the answer for letter A. That's our displacement function. Now, for letter B, it says, how far did it travel from 2 seconds to 7 seconds? So now what we have here, we call these parameters. We now have parameters. We know we're measuring from a time of 2 seconds to 7 seconds, and we want to know what the displacement is from 2 to 7 seconds. So we kind of use a little, well, it's not really a different notation. It's a new notation for a lot of you probably. So this is what it looks like here. So we're doing the same thing that we did before when we were finding the position function with respect to time from the velocity function. But now we have parameters, okay? So since we're going from 2 to 7 seconds, we actually put these on our integral sign. All right. Sometimes you'll hear them described as parameters, boundaries, things like that. Okay. It's just what we're going to actually plug into the equation. So I'll show you what I mean by that in a second. So again, we already know what the antiderivative of this is because we found it over here. So now we can just plug that in. So we get t squared plus c, and then we're evaluating from 2 seconds to 7 seconds. I like to put a big bracket right here. That's how I learned it when I was your age. So I don't know if that's how they still teach it, but that's always how I write it. So I'm evaluating from 2 seconds to 7 seconds. Kind of weird that we go from bottom to top. I don't really know. But that's just how I was taught how to do it. So now what we want to do is we want to actually plug our times in. Now, just like any other delta, because remember, this is a change here. So we're going to do final minus initial. So what I mean by that is we're going to plug 7 into this whole thing first, and then subtract, and then plug 2 into it. So it looks something like this. So I have 7 for t, that's what I'm plugging in my 7 seconds for t squared plus c. So final minus initial, which is 2 seconds squared plus c. Sorry. Keep accidentally clicking. So see how we have 49 plus c minus 4 plus c. And so since I have c minus c here, my c term, my constant term, actually cancels out. So this is why whenever you have this is called a definite integral. When you have parameters, when you have boundaries, here we're going from 2 to 7. When I have those boundaries, it's called a definite integral. You don't have to add c. Okay, because it just drops out from this term because of the math. So we end up getting 49 minus 4, which ends up being 45 meters. So again, this is an indefinite integral here because we don't have any boundaries. This is a definite integral because we do have boundaries or parameters. I've heard them used, both terms used. Now, another thing that we want to remember is that we are summing up those little quantities under the curve here, okay? So it is kind of weird. It might seem weird at first that we're using this subtraction when we're supposed to be summing up these discrete quantities. But the reason for this, and I have a bunch of writing down here, so I'm sorry, but what we're doing here is we are finding the area from 0 to 7 and then subtracting the area from 0 to 2. All right, so that's why we're subtracting the 2. It's final minus initial because we're subtracting that little bit. A lot of the time you will see that we are evaluating from 0 to 7, not just 2 to 7, but you know, the parameters could really be anything, okay? All right, let's do another example. Okay, so I have 2 particles move along an x-axis. The position of particle 1 is given by x equals 6t squared plus 3t plus 2 in meters and seconds, and the acceleration of particle 2 is given by acceleration is equal to negative 8t in meters per second squared and seconds. And for particle 2, at time t equals 0, its velocity is 20 meters per second. When the velocities of the particles match, what is their velocity? Now, this is the example where we are actually going to find c that I was talking about earlier. Also, it's a lot of information kind of thrown at you at once. So just first and foremost, we want to kind of just remember we have 2 particles, okay, particle 1 and particle 2, and we want to know when the velocities of the particles match, what is their velocity. Half the battle in physics, and you can probably see already, is that the problems here that we're going to be solving are word problems. which everyone hates in their math class. So these are all the problems that you hated in math class. But if you apply just kind of a set of steps and a set of rules when you're doing these problems, it makes them much, much easier. One of the first rules I have is to remember what we're actually solving for. So I always ask myself, and I'm going to go over this more when we go over our next part, when we actually start the school year. But one of the things I always ask myself is, okay, what am I actually solving for? Because sometimes it gets kind of lost in the solving of the problem. Okay, so I want to know when the velocities of the particles match, what is their velocity? So what this tells me is I need to find a velocity equation for both of these particles, and I need to set them equal to each other because they're going to match, which means they're equal. Okay, so it says the position of particle 1 is given by a position function. If I want to find velocity from position, what do I need to do? If you said take the derivative, you're correct. All right, so I need to take the derivative of that first function. That's easy. We learned that at the very beginning of this lecture. So I'm just going to take this exponent, multiply 6 by the exponent, subtract 1. I get 12t plus 3. All right, so the velocity for particle 1 is going to be 12t plus 3. I know I did that very quickly, but this lecture is long enough as it is. And then for particle 2, now we are given the acceleration. All right, so how do I find velocity from acceleration? If you said take the antiderivative or the integral, you are correct. Okay, so now we're going to take the integral for particle 2's acceleration to find the velocity. Okay, so I know that this is like negative 8t to the first power. So again, we add 1 to that. So that's negative 8t squared. We're then going to divide by 2. So negative 8 divided by 2 is negative 4. Don't forget to add the c. So we end up getting that the velocity function for particle 2 is negative 4t squared plus c. Now, I told you at the beginning of this problem that we're going to learn how to solve for c when we're given some information. Do you see how at t equals 0, so when t is equal to 0, the velocity of particle 2 is 20 meters per second. This is that information that we are going to use in order to solve for c. So all we do here is we're just going to plug 0 in for t here in this equation, and then we're going to plug 20 meters per second in for velocity in this equation, because at a time of t equals 0, we know that the velocity here is 20 meters per second. So plugging that stuff in, we end up getting 20 meters per second is equal to negative 4 times 0 squared, which is just 0, plus c, which tells us that c is equal to 20. So then we can plug that into our equation, and we now have an equation for velocity of particle 2. We couldn't just leave it with c. It's too many unknown variables. All right, we didn't know what c was, so we had to find what c was. All right, now I have my two equations. I want to know, again, we want to know when the velocities of the particles match, what is their velocity? So since they match, I now want to set these equations equal to each other. So velocity of particle 1 equation equals velocity of particle 2 equation. We get 12t plus 3 equals negative 4t squared plus 20. I rearrange and see that I have a quadratic, which you can just plug it into your handy dandy calculator. The program that Miss Halstead probably had you guys put into your fancy calculators. I personally always just use a for function. So I always do this longhand. Maybe it's because I'm old school. Maybe it's just because I like singing the quadratic formula song. I don't know. X equals negative b plus or minus square root. You guys all know it. Come on. B squared minus 4ac all over 2a. Amazing. I know. Notice how I just put x because that is what is in the quadratic formula song. But remember, this x in this case is t for time. Okay, so don't forget that. So solving this magic, we end up getting two answers. So our x is equal to 1.05 or negative 4.05. Which one of these do we throw out? What do you think? If you said the negative, you're correct. Okay. Yes, we throw out the negative 4.05. Why do you think that is? Think about what x is in the quadratic formula. I just told you. Remember, x is time. It doesn't really make sense to have a negative time. Now, it's not like illegal, but a negative time would be like before you hit the, start button on your timer. 4.05 seconds before you did that. That is one of the answers. Doesn't really make sense, right? So we're going to throw that one out. We're going to use the time of 1.05 seconds. So are we done? Is that our answer? No. Okay, remember, we want to know when the velocities of the particles match. What is their velocity? We know what the time is when they match. It's at a time of t equals 1.05 seconds, but we still don't know what the actual velocity is, which is what we're actually trying to find. So what we're going to do is we're just going to plug this 1.05 seconds in for time in one of the equations. Doesn't matter which one. I'm just going to use the velocity for particle 1 just because the math is a little tiny bit easier. We get velocity is equal to 12t, so I plugged in 1.05 in for t, plus 3, and then solving here we get 15.6 meters per second. If you plugged this in, if you plugged the time of 1.05 in for the velocity equation for particle 2, you would get the same exact thing. So that's a good way to check your work if you ever have extra time on like a test or something like that, okay? All right, finally at the end. Our key takeaway here, okay? Key takeaway. When we're going from a position function with respect to time to a velocity function with respect to time to an acceleration function with respect to time, we are taking a derivative. What we are doing here is we are finding how that function actually changes with respect to time. We're finding the slope of the curve, okay? So on a position versus time curve, the slope is going to be velocity. On a velocity versus time curve, the slope is going to be acceleration. Now, if we're going backwards, if we're going from acceleration with respect to time to velocity with respect to time to position with respect to time, we are taking the antiderivative or the integral, which is the area under the curve, right? And remember how to actually do those things. For the derivative, we use the power rule. For the integral, we use the anti-power rule, and we have that weird C thing. I will tell you that in physics, most of the time, we kind of just drop C because we do get parameters, so you don't really need it most of the time, okay? So don't worry about it too much. But I did want to teach you about what it is and how you can find it and things like that. And that is it, okay? That's calculus. You're welcome. I'm just kidding. I do have a little tiny homework assignment for you for this. At the beginning of the worksheet, there is kind of a write-up of all the stuff that I went over, kind of in a little bit of different words. It's written by someone else. So if you are still having trouble with this, skim over that explanation too. It does help to kind of hear it in other words a lot as well. And like I said, I will try to put up some videos on this stuff because I know that it is a lot of information if you've never heard it before, okay? So there's a short worksheet online that is part of your summer work. I hope you guys are having a wonderful summer, especially, despite the circumstances. But I look forward to our year and I will see you soon, all right? Bye guys.